So I think we're live right now. Let me check. Okay, yeah, I think I'm live now. Okay. So let me okay. Okay, I'm gonna wait for a bit until I get a few more viewers and then I'm gonna start. Okay, so I think I can get started now. Okay, so what I'm gonna do is I'm gonna go ahead and put a timer up here. So let me search up timer. See if, okay. All right, so I have my timer set here. So what I'm gonna do now is I'm gonna go ahead and open the International Math Olympiad website. And if I click on the IMO competitions, or probably, yeah, if I click on this problems tab, then I should see the problems immediately. Okay, so I guess I'm gonna get started right now. And what I'm gonna be doing is I'm gonna go through each problem one at a time, or maybe go back and forth between them. And I'm gonna be solving them live on this whiteboard right here. So I'm gonna yeah, I'll be doing all my work up here so you can see how I'm solving them. All right, without further ado, let's go ahead and get started. Let me go ahead and click the problems and open them, and I'll start the timer. Okay. Okay, yeah, here are the problems. And the timer starts now. Okay, so there are 26 integers greater than 1 written on this blackboard, and they're not necessarily different. And Confucius chooses two different integers which are greater than 1, or they're just two integers, I guess, and replaces them with GCD and LCM over GCD. And regardless of the choices of this person, after finally many moves, we want to prove that exactly one integer is greater than n. So, okay. Oh, there are 2026 integers here. So, I think I see what's going on. Let me go ahead and screenshot this problem and then put it on the whiteboard. Okay, there we go. So what we're trying to do now is, so we have 2026 integers greater than 1, and so we're replacing any two integers. We're choosing two of them and replacing them with these guys here. And we want to prove that at some point the board will just stay the same. It will only have 1, 1, 1 all the way to n. And then this value of m is independent of the choices that he makes. So we're basically replacing, suppose that we have dx and dy are two numbers, so that's where d is the GCD. Then we're basically replacing dx and dy with d and then xy. So what exactly stays the same here? Okay, let's try an example. So suppose that I have, let's start with two integers on the board. Then we're gonna get, suppose we start with like, I don't know, suppose we have 14 and 34. And yeah, you lost the game. Then the GCD is equal to 2, and the LCM is equal to 14 times 34 all over 2. And then we have to divide that by 2 again. And then this becomes 119. Or, yeah, 119. And then when we take the GCD, we end up with 1. Okay, so the two integers case was like pretty simple. Let's try the three integers case. I look-y think that something like 6, 10, 15 might be interesting, because all their GCDs are pairwise different, but their complete GCD is 1. Okay. So okay, so let's first try doing it on 6, 10. Then the GCD is 2, the LCM is 30, I believe, and this becomes 15, then 15. And let's try moving on 15, 15 now. If we end up doing this, we end up getting 2, okay, so GCD of these two is 15. Oh, and then this LCM over GCD is equal to 1. So GCD equals 1 is not the only way to get 1. We could have that the two numbers are equal, making the GCD equal to LCM. And yeah. So we can't do anything with this number now. Wait, what if we use induction? Because if we can show that one number will always become 1, if we can show that there will always be a number that's equal to 1, then that means that we're done automatically. Because if we have a bunch of numbers here, and then we make one of them 1, by induction, we can only apply on these rest, and therefore we will have 1, 1, 1, 1 all the way to 1, and then an m here. Okay, so that would solve part A if we can show that there will always be a 1. But then part B is interesting. Let me not get ahead of myself and let me calculate the number here. So it seems like the number here is going to be like 1. So it seems like the magic number here is 30. Okay. Then we have 131. So now let's go ahead and try okay, so let's try dude, I hate Microsoft. Okay. So let's try 10 and 15 first. So now if we do 10 and 15, it becomes 6, 5. The GCD is again equal to 30. So then it's 30 divided by 5, which is 6. And then if we move on 5 and 6, then it becomes 6, 1, 30, I believe. And then we have the GCD of these two is equal to 6. And then we have the LCM is 30, so it becomes 6, 1, 5. And finally, we get 1, 1, 30 again. It definitely feels like, I don't know. It seems like the magic number here is just equal to the greatest common, is equal to, the least common multiple here. But I actually don't know. Because it could be something else entirely. Let's try out like 8 and 20. Because that might be interesting. So the greatest common divisor of these is 4. And the LCM is equal to, I believe, it's 40. And we divide it by 4. So that's equal to 10. So now we have 4 and 10. Then the greatest common divisor of these is 2. And then the LCM is 20 this time. So we get 20 divided by 2 is 10. And then we have 2 and 10. Then the greatest common divisor is 2. Then we get 2 and 5. And finally, that gives 110. So 10 is our magic number now. Huh. That's interesting. Wait, am I doing everything correctly? So we have the greatest common divisor is 4, and the LCM is 40. So LCM over GCD is just 4. And then the GCD is 2, the LCM is 20, so that's 2, and 20 over 2 is 10. So yeah, it's not the greatest common divisor. Wait, because we have these GCDs and LCMs, and we have that this number here is kind of similar to this one and this one, I guess we could try using we could just try solving the problem prime by prime. But I don't know if this will work. Yeah, this may or may not work. Okay, so suppose that if we rephrase it in terms of the primes, it might become something different. So suppose we have a bunch of numbers like A1, A2, all the way to A2026. Then if we operate on A1, A2, we replace them with minimum of A1, A2, because that's the VP of the GCD. And then this one becomes like max minus min. So if we're assuming that A1 is less than A2, then we just replace them with A1, A2 minus A1. So we want to end up proving, I guess, that all of these numbers end up collapsing down into some number than 0, 0, 0, 0, 0. The problem is for the primes that might not line up. This could probably be solved if we solve it for each prime, and then we have a bunch of other things. And then if we solve it for each prime, then all the numbers on the board are relatively prime, and then all of them just become 1 immediately. So we want to prove that if we operate on this list here, and these are non-negative integers, and yeah, if we prove that they're all, if we end up getting something 0, 0, 0, 0, then we're set. Hold on just a second. Okay, let me rechat. Oh my goodness, 2 IMO team members are inside my chat. Okay, anyways, so maybe some sort of invariant, I don't know. Let's start off simple and try out like probably 1, 2, 3. Then this one becomes 1, 1, 3, and then if we apply on these two, then we get 1, 1, 2. Wait, this really feels like the Euclidean algorithm. Yeah. Yeah, wait a second. Is this just a Euclidean algorithm? Because if it is, it would be hilarious. Yeah. Like the V2 of this is 3 and the V2 of this is 2. And the greatest common divisor of 3 and 2 is 1. And that's 1 here. And then if you have, then for the V5, you have this is 0 and this is 1. And the greatest common divisor is 1. Wait, this might be it. This might be it. Okay, so because the sum just keeps decreasing and decreasing, we're going to get to a point where only, like, we're going to be stuck at some point because all the numbers we have on the board are greater than 0 and the sum just keeps decreasing. So, but yeah, the sum is monovariant. So that means that the sum of the numbers on the board is just, yeah, it just keeps decreasing. Why did I say that twice? Anyways, so what we end up with is, because we end up stuck with 0, 0, 0, by Euclidean algorithm, this number has to be GCD of A1 all the way to A2026. Well, this might be it. Okay, and now that we have all the primes are in different spots, we have that all the numbers are relatively prime. So suppose we have like relatively prime numbers A1 all the way to like A2026 now. I'll call them B so that I don't get confused. Then we just apply this move every single time. And what we end up with is B1 all the way to b 2026. So I think this solves a problem, because I think that the fixed number on the board is if we have the numbers like a1 all the way to a 2026 to start with, it is like 2 to the power of GCD of nu 2 of a1 all the way to nu 2 of a 2026. And then you do this for all the other primes. Okay. Wait, let me write this up to make sure that I actually solved it. So, yeah. Oh, I made a writing error here. Okay, so I think I finished the write-up. I honestly think this is a really, really nice problem. Like, I especially like the idea of using the GCD with all of the VPs. Because usually the thing that you do with VPs is you have a GCD, or whenever you have a GCD, you end up eliminating the VPs. And by eliminating the VPs here, we end up getting this new problem, which actually involves GCDs again. And when we involve GCDs again, that's the part I really, really like. So it's kind of like you have like a GCD inside of a GCD, which is very, very strange. Okay, I'm gonna take like a 5-minute break and look at the chat, and then I'm gonna look at problem 2. Okay, so I've taken an hour so far. Oh. Wait, it's not been an hour, has it not? Yeah, it's not been an hour. Wait, what is this timer doing? Wait, chat, what time did I start exactly? Because I think this timer just sped up in time. Okay, so I might have set it for 4 hours. Oh, I did set it for 4 hours, 30 minutes. Does anyone know what happened here? Hi, Eric. Hi, Zongshu. The two ways to interpret GCD mean in a lattice and generator of an ideal. This is true. But I'm talking about like in when you're looking at specifically like Olympiad number theory. Wait, do you know what time exactly I started? Oh, I've been live for like 35 minutes, so I'm gonna assume this has been going on for 30 minutes. So I'm gonna go ahead and set up a timer on my system, and I'm gonna set it for 4 hours. Okay, so we can't see the timer right now, but it's a 4-hour timer up here. And yeah, you can probably base it off of the live stream time. If the live stream time hits around 4 hours and 35 minutes, then that's approximately when the time is up. So yeah, the live stream time is basically the live stream timer is just basically my timer for this test. This is literally what the problem is, LMAO. Wait, what? All right, I'm gonna go ahead and start the timer and then start looking at problem 2. Okay, so I'm gonna go way down here, so that's behind. Okay, so problem 2. Oh my goodness, it's a geo. Okay, let me go ahead and screenshot it. Oh my goodness, it's a geo. Problem 2 geos are so back. OM equals ON. Okay, let me get my... Okay, So we have our triangle ABC here. And M and N are the midpoints of the sides. So that's M, that's N. Then points K and L are chosen inside the BMC and BNC. So maybe K could be here. And then K is inside ABL and L is inside AKC. So maybe something like this. Okay, so suppose that KBA is equal to ACL, LBK equals LNC, and LCK equals BMK. And if we have that O as a circumcenter up here, then we want to prove that OM equals ON. So ABK equals ACL. I guess this could mean that if you, that if you extend the sides here, then this quadrilateral here is cyclic. That's the only thing I can really think of. LBK equals LNC. Oh, LNC. So it's equal to, oh, I meant to put this one here. So it's LBK is equal to LNC. ACL, and that's NCL, and then LNC. So that means that this angle here, so angle CBL, is equal to B minus the sum of those two angles. So that's like B minus 180 minus, I think that would be angle NLC, which is B minus 180 plus angle NLC. But I don't know if this is useful or not. I think I'm just saying random stuff right now. Okay, let's try something different. You know what? I'm gonna go ahead and draw in the angles just to be sure. So I'm gonna erase all this. the line and okay, so the line BN is not needed at all. Neither is this line here. I can just clear that. Okay, so first we know that I'm going to mark this in this color. These two angles are equal. I'm going to redraw this diagram. So first we know that these two, I need to change the color. So we know that when we draw this in, and maybe L should be over here, then we know that these angles here are equal. And then LBK is equal to LNC. Okay, I drew the diagram slightly wrong. So what if L is further down here? I think L being here is reasonable. So we now have that these angles are equal. Then LBK, so suppose that's this green angle, is equal to LNC. So if then it's equal to this angle here. And likewise, if I construct this line here, then I should probably construct this one as well. Then these blue angles are equal. And the end goal is to prove that if O is a circumcenter of AKL, then OM equals ON. I've seen this type of thing before where you can prove that the power with respect to M of the circumcircle of AKL is the same as the power of N. This is like that 2009 IMO2, so maybe we could try using that, especially since this circumcenter seems very out of the blue, so to say. So what do we do? We also haven't used the fact that they are midpoints. Yeah, so I want to go back to this idea earlier where I extend these two lines here. And suppose you meet at X and Y. How do we connect this angle here to this angle? I was considering taking a homoscity centered at A that sends M to B and N to C. But that just makes it a bit more complicated because even though M becomes B and N becomes C, we get those 2 points out there. Okay, this might be a complete this might just be out of nowhere, but what if CLK is similar to MKB? Obviously, it doesn't look like it in the diagram, but if it is, then I'd be happy. Because it definitely appears that LKB is similar to CLN. So we want to prove that this is like 180 minus red minus green. So that's 180 minus red minus green. And this is B minus R minus G, where B is the angle B. No, I don't think this will work. This is 180 minus green. Wait, I think I might know where this could be going. So if I intersect AK and AL with the sides, this will make it a bit messy, then it's equivalent to prove that the perpendicular to L and the perpendicular to K meet on the perpendicular bisector BC by taking a homotheteous scale to A. But again, this doesn't seem really helpful, because we still have those relations with the midpoints. So basically any point on this line here, we want to show that the line here is just, or actually we just want to show that the antipode is the on the perpendicular bisector. Oh, hold on. If I intersect K with this side here at this point X, then this one here with point Y, then wait, I think I like where this is going, because we let this be X and let this be Y. Then because these green angles here are equal, we know that BX and L is cyclic. Because the blue angles are equal, we know that CYMK is cyclic. And because the red angles are equal, we know that BXYC is cyclic. Yeah, I was considering using radical center on these two circles, but the problem is that, the obvious problem is that these two circles don't really have a nice radical center, or that these two circles don't have a nice radical axis. And we also know that by Green's theorem that X, Y, M, N is cyclic. Oh, hold on. The radical axis becomes a lot nicer, I think. Okay, wait. If you apply radical axis on these three circles here, then you get that xn and ym meet, and the radical axis of the two circles end up meeting at a point on the radical. Wait, so A lies on the radical axis of the two circles. Wow, what a surprise. So A lies on the radical axis of the two circles, and so does this other point here. I'm going to go ahead and highlight the quadrilaterals in purple so I don't forget what they are. So the line through A and this point here is just the radical axis. Oh, just a second. There we go, I'm back. Can we say anything else with these cyclic quadrilaterals? Wait. Angle XLB is equal to angle XNB, which is angle ANB. And this angle's fixed. Wait a second. So hear me out. So if I extend this line here, oh, let me mark it in orange. So if I extend this line here and end up letting this circumcircle intersect this line CY again, at this point L prime, then L prime also satisfies like the problem condition. Technically it does. Because I mean like the points L and L prime are kind of equivalent. Which would mean that I think this would mean that AL prime KL is cyclic. Which seems completely random. Oh yeah. I think I know that, okay, so if I extend this line here and then construct the other circumcircle, so this humongous one, and they intersect somewhere like over here, then this is a very, very bad diagram, my bad. But like if I intersect it at this point K prime, then KL, K prime, L, and A should be all concyclic. And I know that KL, K prime, and L are concyclic because if we let this intersection point be Q, I actually don't know how I never labeled this point before. But because if we label this intersection point Q, then KQ times QK prime by that one cyclic quadrilateral is equal to YQ times QC, which is XQ times QB, and that is KQ prime. And that is, LY times LQ times QY. Okay, so KL, K prime, and L prime are concyclic. But the obvious question is to show that A also lies on this circle. Yeah, I think that my motivation for like keep this working out, I have no idea if this will work out, but like my motivation for doing this is like the points L and L prime are equivalent, so the problem statement should still hold if I replace L with L prime. Or something like that. I actually don't know at all. I wonder if it helps that A lies on the radical axis. Okay, so one thing I still haven't used yet is the fact that M and N are the midpoints of the sides. Oh, wait a second. So we know the power of A with respect to this circle here. So power with respect to omega 2 of A is equal to, that would be, if we let this intersection point be Z, then AZ times AC. But the power with respect to omega 1 is equal to AX times AN. So that means that this point Z is actually the midpoint of AX, which is really surprising. So in other words, if we construct the midpoint Z of the side AX, then this entire circle here is, then Z lies on this orange circle. And yeah, the diagram is becoming worse by the day. Like now our circle has like a vertical side. Actually, let me try redrawing this circle. That might make it easier. Then it doesn't pass through K. I think this diagram is just cooked. I'm just gonna draw it like very, very weirdly like that. You know what, screw it, I'm gonna draw a new diagram. Hopefully it will be easier to draw this new diagram given that I know a lot more information. So then M and N are on the sides. And we have the points X and Y up here, I know, such that this is cyclic. And I constructed X and Y with that in mind. So if I draw in those two lines, let them intersect at a point Q, and then A and B is this length here. So X and B, then so if I draw that in, then this is the point L. Actually, that's inaccurate. It's kind of lopsided. So if I can draw this in correctly, this should be good. In which case, this is L. And then I have to draw in so BXN, then CYM. So that's CYM. Then YM, and then it intersects this side here. Okay, surely this is a bit better. Actually made a big mistake. I need to draw these circles in a different color so that I can look at them more easily. And this does not pass through the points. And I erased line CY in the process. This is L, this is K. That's the circumcenter. We want to prove that it's equidistant from M and N. Okay, cool. Okay, now I can go ahead and re-highlight these quadrilaterals. There, 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 there. And there, 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 there. And I constructed them in mind with them being cyclic, so hopefully this is better now. And these two circles seem very wrong because A is not on the radical axis. I'll see if I can redraw the circles so that they actually are on the radical axis. Okay, this should be a bit better. So that AQ is a radical axis. Then I draw on these guys, and they intersect at L prime and K prime. Okay. Oh yeah, I also know that I guess I also do know that it intersects at the midpoint, so we'll make these circles. Okay, let's try restating the problem. Because, like, I might be going too far in a wrong direction or trying to overcomplicate it. It feels like I have all the main constructions. Okay, so let ABC be a triangle, and let X and Y be points on AC and AB such that BCXY is cyclic. And let the two segments BX and CY intersect at Q. Let the circumcircle of BXN intersect CY at point L, and let the circumcircle of CMY intersect segment BX at point K. We want to show that M and N are equidistant from the circumcenter of AKL. Yeah, if we can prove that A lies on the KL prime circle, then we're set. Or we might be set, because then we eliminated the point A from the problem entirely. Perhaps. Okay, if I let this point be, suppose M prime and N prime, and because AXY is similar to ABC, we know that when we do this opposite similarity, M prime gets sent to M and N prime gets sent to N. So this means that, like, let me switch to a different color now. That angle YM prime X is equal to angle BMC. And Ym prime X is just Ym prime C, which is, oh yeah, that's just going backwards, my bad. No, Mn prime is parallel to BQ. Oh, so Mn prime Kk prime is an isosceles trapezoid. Yeah, so L prime NL is an isosceles trapezoid. Oh, wait. Okay, so because Ln N prime L prime is an isosceles trapezoid, the perpendicular bisector of LL prime is just NL. So that's the perpendicular bisector. And then the perpendicular bisector of the other one is MM prime. And because Mn prime, M prime, N is cyclic, that means that the circumcenter of KL, K prime, L prime does in fact lie on the perpendicular bisector of Mn. So yeah, if we prove that A lies on the circle, we are set. Oh, what a finding. Yeah, this does seem like a really, really nice finding, but again, I think I'm overcomplicating things way too much. Okay, please, let me prove that AL prime KL is cyclic, and let me just end the problem here. Oh my goodness. Please let me finish the problem. Oh yeah, I guess that because of this perpendicular bisectors fact, the fact that the center here is just a circumcenter of mn m prime n prime, we have that if like this point O prime here is a circumcenter of BCXY, then O should be the midpoint of that thing. Let me put this O point. O prime. So I wanted to add in the midpoint of BY here and show that A is concyclic with that point, that point, and that point. Again, very bad diagram, so Hmm. Okay. Okay, so approximately 2.5 hours remaining, and I've reduced it to this one thing. Let's construct in this midpoint here again. Okay, let's try focusing on BC XY for a second. And then L lies on the circumcircle of BXN. Okay, let's go ahead and look at this like sub-diagram here. So you have like a cyclic quadrilateral here. That's A, that's Y, X, B, C. Then you construct the midpoint of CX. And then you look at the circumcircle. This is N. Or actually you look at the midpoint of AC, so that's N. And then you consider the circumcircle of B and X. And also if you let O be the center here, you also look at the circumcenter of, you also look at the circle with diameter AO. And the question here is, must the radical axis of these two circles be the line CY? C lies on that radical axis because if you let, like, as I said earlier, Z be this midpoint, then you know that the circle with diameter AO is just AOZ, so the power is CZ times CA, and that's equal to CX times CN. So C lies on the radical axis. The grand question is, does Y? It also passes through this other midpoint here. So the power with respect to the circle with diameter AO of Y is half of A, so 1/2 of AY times YB. Then you have the circumcircle of B and X. How do we find the power of Y with respect to that? Like, if we could show that these midpoints here are also collinear, midpoint of AY, midpoint of AC, B and X. So wait, this just does it. Oh, I think I solved it. Because, okay, so basically, so we have that this point midpoint AY here, we have that if we, like, we have this sub-diagram here. And when we have the sub-diagram, we can prove that AO prime LZ is cyclic, because we can do this by proving that CY is the radical axis of the circle with diameter AO prime, which is a circumcircle of AO prime Z, and also the circumcircle of B and X. So we want to find the power, and the power of point C with respect to each circle is just CZ times ZA, which is CX times CN. And then the power of Y with respect to both circles is, if we add in this midpoint here, then we have that, then the power with this, respect to circumcircle of bxn of y is if we let this circle intersect here, then it's just the midpoint. So that's the midpoint by power of a point. So that means that the power with respect to that one circle of y is half of this quantity here. And the same thing goes for the other circle, because the foot from O to this side here is just the midpoint of by. Okay, so therefore we prove that AO prime LZ is cyclic. And this also means that, okay, so this means that ALO prime is equal to 90 degrees. And then similarly, AKO prime is equal to 90 degrees as well. And therefore, O prime is actually the antipode of A with respect to the circumcircle of AKL. And because O prime is on the perpendicular bisector of BC by construction, because it's just the circumcenter of that circle, we know that O prime B equals O prime C. And then we take a homophobia scale 1/2 to get that OM equals ON. Okay, but I just need to make sure that we're not going backwards anywhere. Because going backwards is definitely a huge pitfall in this proof. And I don't want to say that I solved it before I confirm that I'm not going backwards. Okay, so the first thing we did is construct the points x and y, and note that bxyc is cyclic. Then we also noted that x and lb is cyclic, as is ymkc. And then we constructed the circumcenter of byxc, which is O prime. And we end up proving that AO prime LZ is cyclic by proving that it lies on the radical axis. Oh yeah, I constructed this midpoint over here in this proof here. My bad. So we can actually just construct this other point W. I forgot to construct that because it was very off diagram. So if I do that, then that, so that's W. Then we note that the circumcircle of AZ O prime W and the circumcircle of BNX has radical axis CY because C has equal power with respect to both, as does Y because of this midpoint observation. And this midpoint here lies on the circumcircle by power of a point. And then we have, anyways, because we have they're on the radical axis, we therefore know that L lies on the circumcircle of AO prime Z, which means that ALO prime is 90 degrees, as is angle AKO prime. And this just solves the problem. Okay, I'll go ahead and write it up. I'm very convinced that this works, but I'm going to take around 30 minutes to write it up, because I want to make sure that nothing goes wrong. Dude, this was like, I have no clue how I didn't see this until now. how I didn't see that circumcenter observation. Barley. Oh. YouTube auto-translated it. That's silly. Wait, how many? Oh, cool. Okay, let me go ahead and launch my whiteboard back up, and we'll write it up. Dude, this solution is so strange. And keep this diagram here in the corner just for my reference. Oh yeah, we never even used the points K prime and L prime. Yeah. But I guess they helped in like finding the circumcenter observation. In a way, this feels a lot like 2024 USAMO problem 5, where there were basically two possible points, and those two possible points gave the main construction. In this case, the two possible points K and K prime and L prime ended up giving the circumcenter that I needed. And then with the other ones, so BX and L cyclic, and then we have YMKC. Oh, and that's why the midpoints are used. Because we're using the circumcenter introduces the midpoints naturally. Of AX, yeah. And this should be O prime. Power with respect to omega is equal to CZ times CA times CA, which is equal to, by midpoints, CX times CN, which is power with respect to omega 2. That's omega, that's omega 1. My bad. Yeah, that's omega 1. Omega 1 of C. And then we also have power with respect to omega of, I think that should be Y, is equal to YW times YA, which is equal to, again by midpoints, YN prime times Y, or YB times YN prime. I should not mix up the order. And that's equal to the power with respect to omega 1 of Y. So CY is the radical axis of omega and omega 2. So, and because we know that L lies on the radical axis and L lies on the circle omega 2, we have L is on omega. And as such, angle ALO prime equals 90 degrees. And similarly, angle AKO prime equals 90 degrees. So that means that that O prime All right. Okay, we solved it. Yay, we solved it. Okay, I'm gonna take a bit of a break right now and look at the chat. Wait, Zongshu, are you still here? What was the first reduction step that I did that you were pointing out to? Okay. Alright, I think I should look at problem 3 now. At least give it a try. There's a good chance I may not be able to do it, but hey, I might be able to sweep, who knows. Okay. Liu Bang and Jiang Yu have a stick of length 1, want to divide it between themselves. Liu marks at most n points on the stick, and then Jiang marks at most n points on the stick. So n and n. Marked points are distinct, then the stick is cut at all marked points, creating a number of pieces. Afterwards, they take turns claiming any unclaimed piece of the stick, with Liu going first. Each player's goal is to maximize the total length of their own pieces. So what's the largest C that Liu may guarantee a total length of, regardless of Jiang's play? Oh, I shouldn't look at the day 2 problems. I should stay up here. I guess I should make some progress on this, or the most I can do. So Liu goes first, okay. Okay, so what if n equals 1 first? Then we have a stick here. And the stick is of length 1. Yeah. Suppose that Liu goes here first. And if Jiang moves inside this chunk here, then Liu just takes that one first and he wins. Or actually, he doesn't win. It's like... it's like very suboptimal, I guess. And then if Jiang moves here, then Liu ends up taking this one and this one. So it's optimal for him to move at the midpoint here. So that if this is x, and n equals 1 case is already kind of non-trivial. Okay, so what's that Liu marks this point here. And that's at point x on the stick. Then Jiang can mark this one here. And then Liu takes that one and that one. So then this total score would be x plus 1 minus y. And that's if y is closer to the end of the stick than to x. And if y is closer to x than the end of the stick in this chunk, then the total length is equal to y. And that's... So in any case, if y is chosen to be in this chunk, then the total length that Liu can claim is at most 1 plus x over 2. Okay. So if I take this here, wait, I should probably put a message in chat saying that I'm that I solved P1 and P2. Okay, so now let's suppose that Jiang moves in this chunk here. So suppose that's y. Oh, and then there are once again two cases. Either y is over here, like very close to that, in which case the total length is y plus 1 minus x. So if y is greater than or equal to, I think that's like 2x minus 1, then it's y plus 1 minus x all over 2. And then when y is minimized, it becomes x, the length is x. So then we get 1 plus x over 2, then x, then if y is in this other is further away, then Jiang just takes the, and we're going to assume that x is greater than 0.5 for our purposes, because it's just symmetric. And then in which case Jiang, then in this case, Liu just claims the length of, oh wait, I messed it up. If y is in this lower half, then we claim a length of x, regardless, because this length is larger. But if y is in this other part, then we claim those other ones. So if y is less than or equal to 2x minus 1, which is less than or equal to, let's see, it would be 1 plus x over, it would be x over 2. Then the total length we claim is equal to y plus 1 minus x, which is then 1 minus x over 2. So I'm going to do 1 minus x over 2. X over 2, then x, then 1 minus x. So that's 1 minus x over 2. And then finally, if y is in the other chunk, where, or actually not finally, but if y is over here, such that this chunk here is the largest, and then it's this chunk, then it's that chunk over here, then we end up getting a length of, okay, if we get x then y, then, okay, so we end up claiming these two chunks, assuming that this length here is larger. So in that case, that it's 1 minus y, and the only way that this length can be larger is if it's y equals 1 minus x. So then in this case, we get x again. And finally, if y is on this side here, then we end up claiming this one and this one. So that's just x again. So therefore, what Luke claims is going to be the minimum of 1 plus x over 2, 1 minus x over 2, and x. We want to maximize this minimum. Okay, let's graph it. So that's 1, that's 1/2. And then this is 1 up here. And then 1/2, 3/4, all the way up to 1. So that's one line, 1/2, then 3/4, then down there, other one, and then finally that. So it seems like the 1 plus x over 2 is always a larger one. So therefore, when we let x be basically as large as possible, we end up getting a length of 1/2. And when x is as large as possible, oh wait, we're looking at the minimum, my bad. We're not the maximum. So something like this. So this is our minimum function. So x is equal to this downward facing line, 1 minus x over 2, when x is equal to 2 over 3. And therefore, the maximum we can obtain is 2 over 3, obtained when taking x equals 2 over 3. Honestly, I kind of expected this. Like, I kind of expected this to happen, where you do it at where the optimal strategy for Liu is to take the points at the equally spaced parts. And then we can claim at least 2 over 3. Somehow. I should probably take the time to reread my problem 1 and problem 2 solutions. Okay, so we first consider prime by prime. And VPM equals X, then yeah, and then we're just using Euclidean algorithm. At some point should be instead at some. Yeah, actually, I guess like at some point works. So then 0 is what terminates. And finally, because we did this process with all the BPs, we get that all the numbers on the board are relatively prime, and their product is that, and then we're done. All right, I guess we can continue looking at it. Let me put the problem up here again. Let me see if okay, now we'll see if the x equals 2/3 work. X equals 2/3. Oh. So what my math says is that this point here, you choosing that when n equals 1 should be the optimal strategy. And then with that, Liu can always guarantee 2/3. So if Jiang moves in this chunk, then Liu just claims the big one. Otherwise, and then if it's closer to this one in the chunk, then we again win. Suppose this over here. Oh, and then this zone here is just 0. So that means that in this zone here, we have that this is the largest chunk, this is the second largest, and this is the smallest. Oh, I think I see what happened here. So because when we're moving in this chunk, we have that it's always going to be, these two are always going to be the largest and smallest in some order, because they form an arithmetic sequence with 1/3. So that's why we're able to guarantee at least 2/3. And obviously when we move here, then we just win. Okay. Now the case the case where n is greater than or equal to 2 is definitely a bit more interesting. So I'm going to put this down for now. N equals 1 gives the answer 2/3. Now let's look at n equals 2. And I could honestly just bash this. I would expect the answer this time to be something like 3/5. Suppose that Liu chooses this point out here and this point out here, where this is 1/5, 1/5. Then Jiang picks 2 other points. And then we choose the largest, the middle one, and the smallest one. What's a good way to distribute these lengths here such that we always have this idea of like the arithmetic sequence? Because it worked out really nicely with the other one. Actually, we cannot guarantee an arithmetic sequence with this one because we have 2, because Jiang has 2 points. Okay, let's just take cases. This will be a humongous case bash. Or it may not be a huge case bash. We'll see. Okay, if Jiang moves in these here, then that means that we can guarantee a length of at least 4/5. And similarly, if we move here. So really and if Jiang moves here and here, we can already guarantee the length of 3/5 as we need. So let's go ahead and assume that there's a point in here. So there are 2 cases we need to consider. One is where we have a length in here, and the other is we have 2 points in here, and the other is we have 1 point in here and 1 point in there. So first, suppose we have 2 points in here, and these are lengths x, y, and z. Then we need to order x, y, and z somehow, and then take the smallest, then largest, then middle one of the 1/5. Yeah. Okay, so the largest one of the 1/5, so the largest one of these 5 is guaranteed to be one of x, y, or z. Because if all of these were smaller than 1/5, then the length of the segment is less than 1. So suppose that like z is the largest one. And similarly, the length of the smallest one must be either x, y, or z. Because if 1/5 of the smallest is the smallest one, then the length is greater. So suppose that x is the smallest. Then either y or 1/5 is the middle one. So if y is the middle one, then we guarantee at least z plus x plus y, which is 3/5. And if if 1/5 is the middle one, so we have something like x, y, 1/5, 1/5, and then z. Oh, and then 1/5 is just greater than y. So that means that we again get greater than 3/5. So in the case where the 2 points are inside the middle of that chunk, we get that 3/5 is possible. So let me take these away. And then suppose that this time we have 1 point in here. I got rid of the entire line. Can I get rid of this one squiggle here? There. And suppose now we have 1 point here. Oh, I have my eraser. And 1 point here. So that's 1/5, 1/5. And I'm going to go ahead and mark these up. So this is going to be x, then y, then z, then w. So x plus y equals 3/5, and z plus w equals 1/5. And we want to do stuff with this. So once again, what's the largest one? Well, the largest one again has to be one of x, y, z, or w, because if the largest is 1/5, then you're cooked. So that means that, suppose without loss of generality, actually we can't assume without loss of generality, because x plus y is fixed, and so is z plus w. Actually, wait, because this length is 3/5, one of x or y is greater than 3/10, and 3/10 is greater than 1/5. So that means that it's already going to be larger than z and w combined. So we can assume without loss of generality that y is the largest one. And then similarly, the smallest one is one of x, y, z, or w as well. And again, we can assume without loss of generality that w is the smallest one. So we have w, y, and then x 1/5 and z in here somewhere. And now we have to figure out which one is the middle one. Oh, z is smaller than 1/5. And yeah, z is smaller than 1/5 because it's inside this segment here. So that means that 1/5 can't be over here. It has to be either z 1/5. Yeah, so z and 1/5 have to be in that order. Wait, actually, wait, let me get some water real quick. Okay. Okay. Okay, I'm back. Okay, so I can now erase this. Okay, so back to this problem here. Okay, so suppose that z is the middle one. Because then that means that this is, yeah. If z is the middle one, then you're fixed. So z 1/5, then x. Then you're looking at w plus. Then you want to minimize x plus 1/5. Or at least John wants to. And because x is a larger one, or John wants to maximize it, my bad. So then by setting x equals 3/10, wait, x has to be less than 1/5. Yeah, x has to be less than 1/5 because x is less than z, which is less than 1/5. Oh yeah, because x is less than 1/5 on the list here. And that means that we want to minimize x plus 1, maximize x plus 1/5. And that's at 2/5, and that gives again 3/5. Okay, so then there's a case where 1/5 is the middle one. And then once again, z is fixed, as is x. Then we want to maximize the length of x plus z. Where we know that x is less than 3/10, and then z is greater than, and z is less than 1/5. So that gives x plus z equals 1/2. Huh. Wait a second. This might not work. This might not be our lucky construction. I erase the line. And then I get rid of that. So what we're saying is that, wait, let me go ahead and enable my pen again. So what we're saying is that if Jiang marks this point here and this point here, basically, or any point super, super close, then this is 1/5, 3/10, 3/10, and then that's basically 1/5 minus some quantity epsilon and epsilon. What we're saying is that we can only guarantee 3/10 plus 1/5 plus epsilon. Okay. So this doesn't really work. So, and it seems like this 3/10 just cooked us a lot. Because 3/10 plus 1/5 is greater than our... Actually, wait. I'm dumb. I am dumb. Because actually, whenever we have our points, because 1/2 is less than 3/5. Yeah. Actually, wait, never mind. I'm actually not dumb. The most that John can confirm in this case, yeah, not trolling. Yeah, sorry about that. Was just blinking there a bit for a second. And then this means that we have to get 3/10 plus 1/5, which is 1/2, which is less than 3/5. And then plus some small pocket change. So let's assume that for now we can. So this doesn't work, and yeah, again the 3/10 is what cooked us. So suppose that we let it be at so that's 1/5, this is 2/5, this is 2/5. And then in this case, suppose that it's like that and that. Or that and down here. Then we clean the 2/5 first, and then we get the 1/5. So the strategy we presented earlier with the 1/5, 3/5, 1 case distribution doesn't exactly work here. So this is very promising. So we have 1/5, 2/5, 2/5. Now let's do the case bash again. Let me erase this. Erase that. So now let's do the case bash. So if I choose 2 points in here, then we again snatch the 3/5 as we need. Otherwise, and similarly, if we choose 2 points in here, we again snatch the 3/5. Actually, we don't immediately snatch the 3/5. So this is again non-trivial. So suppose we have that this is x, y, and z. We want to snatch it, and that's a total length 2/5. Then we know that 2/5 is the largest. So 2/5 plus, and then one of x, y, or z is the smallest. So I'll do plus z. So I'm going to do z, then 2/5. Then what we have left is x, y, and 2/5, and 1/5. And then there are a few cases from here. The first case is where we have 1/5 is the largest, and then x and y are down there. In which case this is 2/15 plus 2/5 plus another 2/15. And actually the most we can guarantee with this strategy is we want to maximize the length of the middle segment, which is x. This length of the middle segment it can be just half of that, so that's 1/5. And then you get 3/5. Then there's a case where 1/5 is in the middle, in which case you get, that is x, then y. Then you already claim 3/5, yeah. And then if 1/5 is on the side here, then you again get 3/5 because it's larger than 2/5 plus 1/5 plus c. Okay, so in this case where they're on the same side of it, or they're on the smaller branch, then we solve the problem. The more interesting case comes when we look at when both of them are in this. Because obviously first Jiang picks this one, first Liu picks this one, then Jiang picks this one. And then what we're left with is Liu picks 2 of the lengths in there. And they have to sum to 1/5, and otherwise you're cooked. And this is not always possible, sadly. Okay. So this means that this once again does not work. Sad but true. What if we try making it like centered? this could be a good idea. So let me go ahead and erase this entire thing. Then we have, we have this line here. This is 2/5 and this is 3/5. So now we have 2/5, 1/5, 2/5. This could be the one that ends up working. And this looks very, very symmetric, so yeah. So we don't have to deal with many other random cases. Anyways, suppose that we have x and the 2 points are here first. Then we have x, y, and z, where x plus y plus z equals 2/5. And this is just basically the same as the case we did earlier, because the 1/5 and 2/5 are swapped. And then I'll mark the ends of these. Now suppose, and the same case is that if they're both at that end. Now what if there's one at each end? Then we have x, y, z, w, and a 1/5 in the middle. X plus y equals 2/5, and z plus w equals 2/5. Can we guarantee that we can always pick 2 of these that sum to at least 3 of these that sum to at least 3/5, the largest, middle, and smallest? Okay, so once again, just like in the other case, if 1/5 is the largest one, then that means that the total length of the stick is less than 1. So that means that one of x, y, z, or w is the longest one. So assume without loss of generality that it's w. And then we also have a smallest one. This time, we actually z, let's assume that z is the largest one. And then we also have, without loss of generality, a smallest one. And sadly, we can't really take cases on that. Oh wait, one of these is also larger than 1/5. So suppose that is zy, and then the other 2 are smaller. So 1/5, then x and w. Suppose. Or something like this. And this z and y can be without loss of reality, and that x and w cannot. So if it's w down here, then it becomes 3/5 as we need. And again, if it's, if it's x, then w, then this might be an issue. So x is less than w, and then y is less than z. Oh, and that just gives a contradiction. So it has to be the w and the x, and that gives 3/5. Okay. All right, cool. Oh, yeah. So now we've solved the case where it's like 1 on either side. So now we can safely assume that there's always going to be 1 in the middle. And this point should be erased here. Okay, so now suppose that we have a point here in the middle, or we have 2 points here in the middle. Then 2/5 and 2/5 are the 2 largest ones, so we claim those. So those are claimed. And then we once again run into the issue. Dang it. Dang it, we ran into the issue again. I think the problem with having two lengths of 2/5 is that Jiang can just guarantee to pick one of them up. And then you're cooked for the 3/5 strategy. So you don't want two lengths of 2/5 in your original construction. Honestly, let's just go for a more symmetric strategy here. So let's go ahead and erase all this. So and let's just split it into 1/3, 2/3, and 2/3. This is just like a last effort strategy before I stop working on this problem. Okay, so 2/3, no, 1/3, 1/3, and 1/3. So once again, there are two cases here. One is where they are both on the same segment, so we have x, y, z. And in this case, we guarantee a length of at least 1/3 plus 1/9, which is 4/9, which is sadly not greater than 3/5. And that means that 3/5 is probably not the answer. I'm very convinced that 3/5 is not the answer for n equals 2. And then we have the case where they're on different segments. So x, y, z, w. Each of their sums is 1/3. So it's going to be y, z, 1/3, x, w, something like that. And then that gives a sum of 2/3. Oh wait, it's not 4/9, it's 5/9. And still that's not greater than 3/5. So the answer in this configuration is 5/9. But like the problem with doing the equidistant strategy is that this does not always work. For example, when n equals 1, as I worked out earlier, we can do better than this. We can do better than just looking at the 1/2 case. Because we can always guarantee a length of at least 2/3. Weirdly enough. Actually, wait, I'm starting to question even that now. Actually, yeah, we can, my bad. I was gonna say 1/1 and 1/5, 1/5, 3/5 as a last effort strategy, but then I realized that this is equivalent to the 1/5, 3/5, 1/5 case I tried earlier. I want there to be a way where I can just snatch away the 1/5. Where I can just snatch away the 1/5. Or snatch away the 3/5, I meant. Just like we could do in the n equals 1 case. 3/5, then yeah, like I genuinely don't know what I should do. N equals 2 is tricky, but once you get the construction, you should get an idea of how to do this. Okay. Yeah, I'm like very convinced that the answer is 3/5 for n equals 2. And then general is like n plus 1 over 2n plus 1 for general n. Like, I agree that, like, if I figure out what the construction is for n equals 2, then this should hopefully generalize to higher n, as does the bound. So, like, I'm still trying to figure out how we can, like, snatch away the 3/5 that we need. And it seems like the bad case happens when Jiang just carves into the smallest segment. Because then you're just plain, like, you're just trying to take things away from the largest segments, and then what's left is you're just battling it all left among the smallest ones. So it's like you're just splitting up the small segment into many ones. And that's where all the strategies are failing. If you're looking at the smallest segment, then you're kind of cooked. So you want to figure out a way to make sure that even if you carve out the smallest segment, you're still fine. And in the 1/5, 3/5, 1/5 case, even if you carving out the smallest segment still gives you the 3/5 that you need. But what if you could... What if you get exactly the 3/5 bound that you need by doing the smallest carved out strategy? What if you consider the smallest one for which this possibly works? So suppose that we have our points. Suppose we have our first point x here and a point y here. Then we end up carving out of these two. And then we take the largest one of these two and the largest two of these guys here. And the largest value of the middle one is 1/2. So you're basically taking 1/2 of this plus 1/2 of this. Or something like that. Or maybe not 1/2 of this. So you're taking like x over 2 plus like... Okay, suppose that this is x, y, z. So x over 2 plus max of y and z. And we're assuming that y and z are both greater than x. So what if you do like 1 minus... So x over 2 plus 1 minus 2x. 1 minus 3x over 2 equals 3/5. 3x over 2 equals 2/5. X equals 4 over 15. 4 over 15. And you have the 2 and then the... So we do 4/5, 4/15, 4/15, and 7/15. Then we claim the 7/15 immediately. And then we look at the... So it becomes like... This might work. Doing 4/15, 4/15, and 7/15. Okay. So let's go ahead and erase this. Yeah, 4/15, 4/15, and 7/15 might work. Because this, in a sense, is the one that like barely works, if you know. Oh, I'm in eraser mode. So suppose we have like 4/15. 4/15, 4/15, and 7/15. Okay, so if you carve one out of each of these guys, if you carve out 2 points inside this segment, then as I said earlier, you're done. If you carve out 2 points in this segment, then you can do 4/15. Oh wait, so 7/15 divided by 3 is 7/45. Actually, 4/15. Actually, this case is non-trivial because because the largest one could be in the 7/15. In every single case, though, both Liu and Jiang are going to claim 4/15. So Liu is going to claim 2 of these, and Jiang is going to claim 1 of them. So we have 4/15 and 4/15 are in here. And that's x, y, and z. Then Liu claims x and z. And similarly, if they're on the other side, then if it's 4/15, 4/15. So basically, Jiang just claims the outer 2 and these 2 in all cases. So that just gives 4/15 plus 7/15 by 2, which is 8/30 plus 7/30, which is 1/2. 1/2! Oh. Because then Jiang can carve into this one. Ooh. Oh yeah, you're cooked if you had to select only one of these 4/15. Wait, how is this ORs? This doesn't even work. The 4/15 one. Wait, Joey, how does this even work? This is not even ORs because like the 4/15 strategy doesn't even work. Let's see. Okay, back to the drawing board with the carving out idea. So suppose you have x, y, z. Those are our distribution. Then we take these out of the smallest segment. Or actually, okay, so suppose that we have that those 2 are carved out. Then we take the maximum of y and z. Okay, wait, I'm trying to look at this, what happened in this case. So 7/15 was 2/5. 9/15. Okay. I'm slowly becoming less and less convinced that the answer is actually 3/5 for n equals 2. So it's like either carving out of the small segment or carving out of the big segment are the ones that fail. Because if you carve out of the small segment, then at some point Jiang takes the half of the big segments away, and you're only left with the pocket change, and you can't get to the 3/5. And meanwhile, if you carve out of the large segments, then you're left with only small segments to work with. So you want to somehow stop both of those from happening. So x over 2 plus max yz. And then if you carve out of the biggest one, then what you're left with is all of these very small segments. If you carve out of this larger one, then you might get into issues. I think the solution to getting around this is to make the smaller one smaller, the smallest one smaller, and the largest one larger. So if you carve into the smaller one, then you're guaranteed to get the larger ones first. And if you carve into the larger one, then you can still win. So you want this to be equal to like 3/5 somehow. So that means that max yz is equal to 3/5 minus x over 2. So we have x 2/5 plus x over 2, 3/5 minus x over 2. And because we have this, we have x is less than 1/5. And if it is 1/5, then we get 2/5 plus 1/10, which is 1/2. Then 3/5 minus 1/10 is again 1/2. Huh. Oh, I can't subtract. Oh, I'm dumb. That's a minus sign. So we have both of these guys. And in the case where those two were equal over here, that gave the x equals 4/15 case, which sadly failed. So what if we make x like, and we're assuming that x is the smallest. So yeah, x is less than 4/15. So what if x is smaller than that? Okay, let's figure it out. What could be the ones that work? So we have x, then 2/5 minus x, then 3/5 minus x. construction 1/5, 3/5 fails for the same reason that you realize for 4/15, 4/15, 7/15. Yeah, exactly. It's because like you either carve into the large segment or you carve into the large segment, and you're stuck with 1/5 plus. Actually, 1/5 plus 1/2 does work, but yeah, it's 1/5 plus 3. Yeah, so the construction for basically the idea of carving out the large one. So how can we get away with this? So I want x to be like sufficiently small. Wait, actually something weird is happening. Oh, this is x over 2 and x over 2. Yeah. Okay, now we're left, and let's see what other progress I can make in the n equals 2 case. Okay, so let's carve out of the large one. So we have like, oh, why is it moving right? Anyway, so we have that and that. So the largest one of these is so the largest one of these is going to be so we have like 1/5 minus x over 6 or something like that. Actually, let's set x to be like an epsilon. So like instead of like x being somewhere like over here, we have like epsilon 2/5 minus epsilon, and then 3/5 minus epsilon over 2. Then whenever we split this, we're guaranteed that one of these guys is the largest. So if we get x, y, and z, we're still not guaranteed anything. So epsilon is going to be claimed last. That's what we know. Or it might be claimed somewhere like, it's either going to be like last or second to last. Two-fifths and three-fifths. Then the smallest is going to be, suppose that epsilon is like 0 as a joke. Then the smallest is x. No, the smallest is 0. Second smallest is x. then we have either y, z, or 2/5. And if 2/5 is the largest one, then we know that by the pigeonhole principle that one of y or z is at least 1/5. So that gives a 2/5 one. If 2/5 is here and z is there, then okay. Yeah, and 2/5 has to be here in this case. I'm just trying to get a feel for whether this epsilon thing can work out, or this x thing in general. So y 2/5 and z. And we want to look at y plus, or we want to, we want to maximize x. And the maximum value of x is just 1/5. Oh wait, if 2/5 is over here, then you might be cooked already, but depending, this could be not so good. Suppose that then you can cut it like so that this is 2/5. Like, I don't know. Okay, so we have epsilon 2/5 minus epsilon over 2. Then to resolve this case, you just like take like that, and that. And that's like, so this is 3/5 minus some small factor. I'll call it like delta, and then this is like delta, delta, delta. So you end up claiming it should just be delta, delta. My bad. It's like delta, delta, 3/5 minus 2 delta. So you first claim the 3/5 minus 2 delta, then the 2/5, then John claims the 2/5, then you're left with one of the deltas, and then the epsilon. Okay, so you can't like take it to be too small. Okay, this is gonna be a bit more complicated than I thought. And Joey probably saw this from a mile away. Like, Maybe I should have seen it coming from a mile away too. Yeah. So again, let's return to the x, then 2x. Then you have like 2x over 5 minus 1. Oh, it's 2/5 minus 1/2 x. Let's go back to the 4/15, 4/15, 7/15 case up here, because if we go into here, then we claim one of the 4/15 and the other 4/15, and then what you're left with is just then this part here. So you want these two to be like relatively far apart, but not too far apart, because when they're too far apart, the thing with that guarantees that most 2/5 happens. Yeah, like if x is like even reasonably close to 4/15, then it will again fail. Wait, because it seems nice, let's try out x equals 1/5. So 1/5, 2/5 minus 1/10 is 3/10. Then you add 1/5 to that. So then this big guy here is 1/2. Does the carving out strategy here work? Suppose you have like x, y, z. X plus y plus z is equal to 1/2. So we first claim the largest one. If the largest one has length, you can do like 3/10, then 1/10, then 1/10, suppose. Then you do 3/10, then 3/10, then 1/5, then then this gives 3/5. Exactly 3/5. But what if you do like an epsilon? Then you do 3/10, then 3/10, then 1/5, then 2/10 minus epsilon, and then Kohage change. This motivates a general strategy. What if I do, instead of doing, so 2/5 minus 1/2 x, then 1/10, 1/10. Then you start off with, then you claim one of these guys, then you claim the x, and then you claim one of the 2/5, one of the 1/10. So you get 1/2 minus 1/2 x, and then plus x, which is 1/2 plus x over 2, which must be less than 3, which must be greater than 3/5, my bad. 1 plus x is greater than okay, wait, so you 2/5 minus 1, and then you have the 1/10, and then you have the plus x. X over 2. So the most you can guarantee with the strategy here is the formula doesn't match for what I got here, so I think I sillied. Oh, this should be 2. This should be 2/10 minus epsilon and epsilon. Okay, so we first take the 2/5 1/2 x plus the larger of these two values. No. Then you take the larger of plus max of like x, and then 2/10 minus epsilon plus epsilon. We want this to be greater than or equal to 3/5. So max of x 2/10 minus epsilon, I'll reduce that, actually 1/5 minus epsilon must be greater than or equal to 1/5 plus 1/2 x. And this 1/5 minus epsilon doesn't work at all. So this requires x to be greater than 1/5 plus 1/2 x, or x is greater than 2/5. And then you're cooked, because then that's not the smallest segment that you can do. So I don't think 3/5 works. Wow. 3/5 doesn't work. Yeah. Yeah, I know you can set epsilon equal to 0. Yeah, but I'm just saying, like, in case that taking epsilon not equal to 0, it works. But, like, I very, very highly believe the answer is not 3/5 now. Because I just bashed all the cases, and this just gave something really weird. Okay, I have 35 minutes to hopefully figure out a correct solution. Okay, so if the answer is not 3/5, then what is the answer exactly? Okay, I'm gonna do a bit of bashing now. So wish me luck. Suppose that our answer is C, as the problem statement suggests. Then we have X, Y, and Z, and then you have them in this order. by the cutting out principle, we know that x over 2 plus max of y and z, it must be greater than or equal to c. So that means that this has to be like c minus x over 2, and then 1 minus c minus x over 2. And then because x is the smallest one, we know that x is less than 2/3 c. We know x is 3/2 than 2/3 c, yeah. So I originally had 3/5. Actually, wait, hold on. Did I screw something up when doing the 3/5 case? Because then that's the max. Oh yeah, that's the max. My bad. So that means that it's going to be, so this is c minus x over 2. This is 1 minus c minus x over 2. And by minimum assumptions, this means that 1 minus c is less than c, so c is greater than 1/2. Okay, so now we have this configuration here. Now let's see what happens if we... so now let's see what happens if we carve these out. If we take like... if we take like 1 minus c minus x over 2, then what's left over here is 2c minus 1. And then this is c minus, then we can do like 2c minus 1 and 0. Then we pick 1 minus c minus x over 2 first, and we also claim that other one, and then plus 0, plus then either x or c minus 1. Oh yeah, and x is less than or equal to 2/3, 1 minus c. So suppose that the largest one is two c minus 1. Then it becomes c minus x over 2, and then you're cooked. So that means that the largest one has to be x, and this is greater than c. So 1 minus c plus x over 2 is greater than or equal to c. So x over 2 is greater than or equal to 2c minus 1. So 1 minus c over 3 is greater than or equal to 2c minus 1. 1 minus c is greater than or equal to 6c minus 3. C is greater than or equal to 4/7. Is 4/7 might be the answer. Who knows? And then that would mean that we have 2/7, 2/7, and 3/7. Hold on. Okay, so we have 2 sevenths, 2 sevenths, and 3 sevenths. Wait, 4 sevenths is correct? Let's go! Okay. Well, I first need to like prove it. Yeah. Like I was like relatively convinced that the answer might be 4 sevenths. Also, if I do end up solving this on stream, then I'm just gonna count it as like solved with chat. Okay, anyways, so we have 2 sevenths, 2 sevenths, and 3 sevenths. This might be our ultimate construction. Because if we carve out in this one here, then what we're doing is we first take the 3 sevenths, and then we can guarantee to take 1 seventh from here. So that's 4 sevenths. Then from here, we end up carving out. So we first snatch the 2 sevenths and then the 2 sevenths. And then we have to play this game in there. And that's 4 sevenths again. And then if we do this, then this is X, Y, Z, W. So then we had to find out some combination of X, Y, Z, and W, which give at least 2 sevenths. Well, I guess X and Y just do that, but so we know that X and Y are on either side of the 2 sevenths. And 2 sevenths might be at the largest one. So if 2 sevenths is the largest one, yeah, this can be really, really weird because, yeah. Let me resolve this case first. So we first pick the 3 sevenths. That's a given. And then my pigeonhole one of these is, so we have a greater than 1 seventh here and a greater than 1 seventh here, and we just pick that one. So we solved both in this one, 2 different ones. Then we solved both in this one. Now we just have to solve this last one. And then hopefully this will give the construction 4 sevenths. Okay, so as a cheese, okay, at this point I have 25 minutes left. And what I can do is either try finish working this out, but I'm gonna first guess the answer. For the jokes, I'm gonna just guess the answer and just assume that it's 1 point. So if n equals 0, then you can guarantee 1, which is 1 over 1, then 2 over 3, then maybe 4 over sevenths. So conjecture the answer is equal to 2 to the n over 2 to the n plus 1 minus 1. This is my conjecture. And if the answer gets a point, then hooray. But I'm not going to expect anything. So, yeah. Oh, 2, 2, 3 is wrong? Wait, why is it wrong for the same reason? Wait, why does 223 not work? I literally, the things that 223 worked for ended up, that the things that 113 and 447 didn't work for were the things that 223 and that 223 got right. Oh. Oh, okay. So all xx1 minus 2x give 1/2? Oh, okay. Yeah. Okay, so we have this 1 minus c minus x over 2 and then c minus x over 2 here. So if c is equal to 4/7 as I want, then it's x 3/7 minus x over 2 and then 4/7 minus x over 2. Oh wait, this is true. Yeah, the x over 2 plus max xyz principle. I'm trying to find a suitable value of x that works. Because then x is less than or equal to 2/7. Okay. Okay, if I can't get any more progress within like the next 5 or 10 minutes, and if I can't get a construction for a value of x within the next 10 minutes, I'm just gonna call it GG's. But hopefully it's something of this form. But what if I do like 1/7, 5/14, and this is 1/2? And this is of the above form, so it could work. Yeah, if this construction doesn't work, I think I'm gonna call it GG's because I only have 18 minutes left, so. Okay, wait, let me lock in. Okay, 5/14 plus 1/4. 1/4 is greater than 3/14. So if we cut both into the 5/14 one, then we're done. And what if we cut into one of each? Then we start with the 1/2. And because 5/14 over 2 is equal... no, never mind. Oh, this doesn't work. Because you could carve it like here and here. That's 1/14, 1/14. Then this is like 0. This is 5/14. This is 1/2. Then you do 1/2 plus you get the 5/14. Oh, this does work. Wait, what? It literally just barely works. What the hell? Okay. What I meant by GG's is like if I don't get the construction for n equals 2, if this doesn't work for n equals 2, I'm just gonna end the timer and end the mock with 770 or 771. But this like has a chance of working, I guess. Oh, if you carve both into here, then you can like... Can you always guarantee a total length of 1/7? Because I literally only need 1/14. Oh wait, I can just get the 1/14 from either this one or this one by pigeonhole. Okay, so that means that you have to carve into the 1/2 one. Okay, suppose you carve both into the 1/2 one. It's like that. Then you first take the 5/14. Oh, because 1/2 over 2 is greater than 7, my bad. But in any case, you're only left gonna get like 5/14 plus like 1/4, which is, we need a 1/7, and this is a, oh wait, this just does it. Oh wait, no. Yeah, 1/4 is greater than 3/14. What am I doing? Okay, I'm very convinced that 1/7, 5/14, 1/12 works. Wait, so suppose you first grab the 5/14, then you need at least the one, then you need at least 3/14. So if you try taking the 1/7, then you're only going to be left with like this pocket change here. So you want it, so you don't want to take the 1/7, and you want Jiang to take the 1/7. So then you want to take 2 of these guys. And you can always take 2 of them that sum to at least 1/4. So that's that case. If you do this, then you end up getting okay, then 5/14, then you need a 3/14. Oh, and then by pigeonhole, no, you can't use pigeonhole. Oh, this fails. Actually, if we cut one of them here and one of them here, then it's not necessarily the case that you're going to fail. Because what I was thinking is that Jiang could just take this cut here, but then you just claim the 1/2 first. So the only reason why you claim the 5/14 first is if this is here greater than 2/7. And we cut in here as well. So we take the 5/14, and then oh, and then one of these is at least 2/7. So yeah. And then the case where it's like that, then you take this one first. So you first start off with 5/14. No, you first start off with this, then you take then the other person takes that one. And then this one might fail. And I'm gonna be a bit, so if we do like 1/14, so that's then this becomes 3/7. So you first take the 3/7, and suppose that this is there. You first take the 3/7, then the other guy takes 5/14. Then you have like a 1/14 there. And that gets you to 1/2, but you can't take the 1/14. So you have to if you take the 3/7, then you need 1/7 more. If you take the 1/14 first, then you're cooked. If you take the... So that means that you have to take one of these ones first. And then if Jiang doesn't take this one, then he's cooked, so he has to take this one. So all in all, Jiang takes 5/14 plus 1/14, which is 4/7. No. 5/14 plus 1 is 3/7, and therefore Liu gets 4/7. So yeah. I still haven't found anything inherently wrong with this construction yet. And I think this still works if you take the cut to be closer to here. Now the main culprit that I'm wondering about is if you have two cuts in here, like that. Then I actually wonder what you're going to do in here. And this may mean that the construction ends up not working. Yeah, I'm just being very, very pessimistic here because, like, I don't know if this will work or not. If it does, then I'll actually be really surprised. Okay, I have 7 minutes left. Can I see if this will work or not? So, yeah, so this is 1/2 again. So this is x, y, z, w. X plus y equals 5/14. Z plus w equals 1/2. Okay, so I think I have a strategy. So first pick the largest one in here to get the 1/4. Then Then if Jiang picks the small one here or this one here, then you just pick this. Then you just pick this one, and then yeah, that just wins after taking the 1/7. Wait, you can't necessarily take the 1/7. So I guess you can do like 1/2 plus 5/28. This is so cursed. Okay, so therefore, if you after you choose that W, Jiang must choose 1/7. Then you can't choose Z, otherwise you get cooked. So you have to choose the larger one in here. And then you have to end up picking one of these guys, and then you're done. So in conclusion, I think that 1/7, 5/14, 1/12 is a valid construction. Can you tell me if 1/2? Can you tell me if the 2/5/7 construction works? I'm pretty sure it does. Oh. Wait, can you tell me why? Also, how are you able to figure this out so quickly? Oh yeah, this is true. Yeah, I guess I found this intuition earlier on, where splitting the sticks is a thing. Okay. Alright, I have 2 minutes left, 3 minutes left on the clock, so I guess I can't really do much at all. Okay, so it's GG's. Alright. So that means that my final score. Okay. So that means that my final score is 7-7, I think 0. Do you think I get a point on problem 1 for getting the get a point on problem 3 for getting the correct answer? Wait, does getting the answer on problem 3 get me a point or no? Oh, yeah. Probably not, yeah. So yeah, probably 7-7-0. That's fine. We still got the second day tomorrow. Okay, I'm gonna go ahead and I'm gonna see if it's fine if I stay up a bit late. Because if I can stay up a lot later, then I'll go ahead and end stream. No, if I can stay up a lot later, then I might live stream me writing on my solutions onto AOPS. Oh, cool. Yeah. Problem 1 and problem 2 are actually such good problems. Like, I really, really like problem 1. Can I talk about this for a second? Like, I really. No, I'm not at math camp set. Sorry. This is why I'm actually able to stream. If I were at math camp, then it would be really, really, really hard to stream. Because then I have to sign in and everything during my live stream. Well, I guess there's like no point of retracting the message because like I already said math camp on the live stream. Wait, should I should I stream me writing up my solutions or should I end stream? Hello, bro. Ohio. Wait, I'm gonna be right back. Yeah, give me a minute. Okay. So I decided that I'm gonna go ahead and end stream. Alright. Also, thank you so much, Joey, for helping me out with this problem 3 and supporting me through this process. Even though I didn't end up solving it, I still made lots of good progress because a lot of it is because of your support. So thank you so much for supporting the stream and supporting me on my problem 3 process. Alright. Alright, I'm gonna go ahead and end stream. Alright. Thank you so much for watching this stream, guys. It was truly one of the greatest experiences ever. And I can't wait to see you guys tomorrow for the day 2. Yeah, thank you so much, Joey, for tuning in and helping me out with problem 3. Alright, bye.